Welcome to our lecture on the least cost method. Imagine you are a business owner needing to ship goods from multiple factories to several stores. You want to save as much money as possible. Today, we will learn a practical step-by-step mathematical approach that prioritizes saving money right from the very first decision, helping us build a highly efficient shipping schedule. Now that we understand the goal, let us look at what this method actually is. In linear programming, the least cost method is a specific algorithm used to find an initial basic feasible solution for a transportation problem. This means it gives us a valid starting plan that meets all supply and demand requirements. It is known as a greedy algorithm because it makes the best immediate choice at every step. By constantly hunting for the cheapest available shipping rate and maxing it out, it builds a very strong and cost-effective foundation for further optimization. To understand this mathematically, we must first define our goal. Our ultimate objective is to minimize the total transportation cost, which we call Z. This formula calculates Z by multiplying the number of items shipped on each route by the cost of that route and adding them all together. Here, M is the total number of origins and N is the total number of destinations. The variable C sub ij represents the cost to ship one unit, and X sub ij is the actual number of units we decide to ship. As we allocate more units to expensive routes, the total cost increases sharply. Since we want to keep the total cost low, we must assign the largest possible values to the cheapest routes. But how much can we actually ship? This allocation formula gives us the rule. The amount we ship, X sub ij, must be the smaller of two available limits: the remaining supply at the origin, S sub I, or the remaining demand at the destination, D sub j. For example, if a factory has 10 units, but the store only needs 4, we can only ship 4. We always take the minimum of the two values. Once we make an allocation using the previous rule, we must immediately update our records. This formula updates the remaining supply at the origin. By subtracting the allocated amount from the original supply, we find out how many units are left in the factory. If this value reaches 0, the factory is empty and we cross out its row. Similarly, we subtract the shipped amount from the destination's demand to see how many more units the store needs. If the demand reaches 0, we cross out its column. We repeat this until all supplies are empty. Before we move on, let us see this with a concrete example. We have a 3x3 grid with supplies of 5, 8, and 7 and demands of 7, 9, and 4. Our strategy is to scan the entire grid for the absolute lowest cost. Scanning the grid, the lowest cost anywhere is 1, located at origin 2 to destination 3. The supply is 8 and the demand is 4. We allocate the smaller number, which is 4. Destination 3 is now fully satisfied, so we cross out its column. Origin 2 still has 4 units left. Continuing with our grid, we look at the remaining uncrossed cells. The lowest available cost is now 2, located at origin 1 to destination 1. Origin 1 has a supply of 5 and destination 1 has a demand of 7. Following our rule, we allocate the smaller amount, which is 5. Origin 1 is now completely empty, so its remaining supply becomes 0, and we cross out its entire row. Destination 1 still needs 2 more units to be fully satisfied. Moving forward, the lowest remaining cost is 3, but we have a tie between 2 cells. In this basic method, ties can be broken arbitrarily. Let us pick origin 2 to destination 1. The remaining supply is 4 and demand is 2, so we allocate 2. Destination 1 is satisfied and crossed out. The only remaining destination is 2. The lowest cost is 3 at origin 2. We allocate the remaining supply of 2. Origin 2 is now empty and crossed out. Finally, we allocate the last 7 units from origin 3 to destination 2. Now that our grid is fully resolved, we can calculate the total cost. We do this by multiplying each allocation by its respective shipping cost. We shipped 4 units at a cost of 1, 5 units at a cost of 2, 2 units at a cost of 3, another 2 units at a cost of 3, and 7 units at a cost of 4. Adding these individual route costs together gives us a final total transportation cost of $54. This is our initial basic feasible solution, providing a valid and cheap shipping schedule. This brings us to an important strategic question. Sometimes you will encounter multiple cells that share the exact same lowest cost right at the beginning of the problem. While you can pick arbitrarily, as we just did, a smart strategy is to pick the cell where you can allocate the largest possible quantity. By maximizing the shipment on the absolute cheapest routes, we ensure that our initial solution is as cost-effective as possible. Let us look at how this works in practice. Let us apply this strategy to a new grid with 2 origins and 3 destinations. The lowest cost in the whole grid is 2, but it appears in 3 different places. Our strategy is to test each one to see which allows the biggest shipment. Origin 1 to destination 2 allows 10, origin 1 to destination 3 allows 5, but origin 2 to destination 1 allows a maximum of 15. Because 15 is the largest possible allocation, we choose this cell to break the tie. Destination 1 is satisfied and origin 2 has 5 units left. Looking at the remaining uncrossed cells, the lowest cost is again 2, located in 2 different places. We test them again. Origin 1 to destination 2 allows an allocation of 10. Origin 1 to destination 3 allows an allocation of 5. We pick the larger one, which is 10. We allocate 10 units to origin 1 to destination 2. Destination 2 is satisfied and origin 1 is completely empty. The only cell left is origin 2 to destination 3, where we allocate the final 5 units. The grid is now complete. With all supplies empty and demands met, we set up our final cost equation. We multiply our allocations by their respective costs. We have 15 units shipped at a cost of 2, 10 units shipped at a cost of 2, and 5 units shipped at a cost of 3. Adding these values together, 30 plus 20 plus 15, we get a total cost of 65. By strategically breaking ties to maximize the use of the cheapest routes, we ensure our starting point is highly optimized. To visualize what this process looks like on paper, let us examine this allocation grid. You are looking at a standard transportation matrix. The origins, O1, O2 and O3 are on the left, and the destinations, D1, D2 and D3 are on the top. The small numbers in the top right corner of each cell represent the shipping costs. The large circled numbers are our final allocations. Notice the arrow pointing to the cell with a cost of 3? This highlights the very first step of the least cost method, always selecting the cell with the absolute lowest cost to begin. We have now covered the full topic of the least cost method. Let us review the key takeaways. First, it is a highly practical, greedy algorithm that builds an initial basic feasible solution by always hunting for the cheapest available route. Second, by filling the lowest cost cells to their maximum capacity, it provides a vastly superior starting point compared to simpler methods like the northwest corner rule, which ignores costs entirely. Finally, while it may not always find the absolute perfect final answer, it creates an excellent, low-cost foundation that saves massive amounts of computing power for further optimization. Great job following along.